In our development of Brownian motions so far, we have worked exclusively on compact time intervals from 0 up to some arbitrarily large but finite time t. As we saw in the last lecture, proving how rough Brownian paths are, it can be a little inconvenient to have to stop at some finite time. And in fact, since the Brownian motion can be constructed on any compact time interval, it's relatively straightforward to extend it to be defined on the entire positive real line. We're going to start with that consistent construction now, and then talk about the properties of that process all the way up to time infinity, using its Gaussian structure. To construct Brownian motion on the full positive real line, we start with the Brownian motions on compact time intervals that we've already constructed. That is, for each positive but finite time capital T, we have the Wiener measure on the path space of continuous functions on the interval from 0 up to t, taking values in Rd, indexed by that time t and also by the starting point x. This is the law of Brownian motion on this time interval, which we began by constructing as pre-Brownian motion, a continuous time Markov process with independent Gaussian increments, and then found a continuous version of that using Kolmogorov's continuity criterion. Well, let's go that same route now. For each such t, we've constructed such a Wiener measure, we've constructed such a process, bt. We want to glue them together to produce a process on the whole positive real line. In order to do that, we're going to need some consistency between the different ones for different t's. So for starters, let's just decide to take t's that are natural numbers. We'll take Brownian motion on the interval from 0 up to 1, Brownian motion on the interval from 0 up to 2, on the interval from 0 up to 3, and so on, and we'd like to glue those ones together. In order to do that, we need to see that there's consistency between the one on the interval from 0 up to 1 and the one on the interval from 0 up to 2 restricted to the interval from 0 up to 1. That's going to follow just from the construction if we start with the pre-Brownian motion again. Remember, that's just a Markov process xt, which is defined on the entire positive real line, constructed via Kolmogorov's extension theorem, to have increments that are independent and normally distributed, where the increment from s up to t has variance t minus s. Now, as we did before, for each natural number, capital T, we can find a continuous version of this process on the interval from 0 up to t. And now we just make the following observation. Do this on the interval from 0 up to t, then do it separately on the interval from 0 up to t plus 1. And we have two processes. Continuous version bt, continuous version bt plus 1. But if we restrict continuous version bt plus 1 to the interval from 0 up to t, that is a version of this pre-Brownian motion process on the interval from 0 up to t. And so is this one by construction. So here I have two different versions of the same Markov process on that interval from 0 up to t. And by construction, they're both continuous. Well, if I have two continuous stochastic processes that are versions of each other, then they are indistinguishable, which is a fact that you're proving on your homework. So that means, in particular, that the probability that there exists even one time in the interval from 0 up to capital T at which these two processes disagree is 0. That means that we can make the following consistent definition. For any non-negative real time all the way up, we define a process bt to be b continuous version indexed by the ceiling of t at time t. By what we showed here, we can take any integer bigger than t here, and no matter which one we choose, we'll get a consistent definition up to a global probability 0 set. Moreover, we know that this process here is continuous on the full interval up to here, and to see that it's continuous even when we reach those jump times when the ceiling of t jumps from one integer to the next, we again use this condition and say, hey, this is just a version of the same one if we put a plus 1 here, and then that's manifestly continuous at the point ceiling of t as well. So in other words, this is well-defined and continuous. On each compact interval, This is a version of this original process by construction, and therefore it has these as its finite dimensional distributions. So it is a continuous stochastic process with these finite dimensional distributions, which means that it is a Brownian motion by our definition. Now we can therefore refer to the Wiener measure now not indexed by a little t, just indexed by the starting point, which is the law of this process. That is to say, it's a probability measure on this full path space, the space of all continuous paths on the full positive real line, taking values in Rd. Now there's one small problem with this. Unlike the path space here, this is not a Banach space, at least not in the sup norm that we've been accustomed to using so far. If you have two continuous paths on the whole positive real line, they can diverge in sup norm from each other as t grows, and so the distance between two paths could be infinite. So that makes it a little bit trickier to talk about the Borel sigma field over this space, but in fact for all considerations that we'll be interested in for Brownian motion, it's usually good enough to restrict to a compact time interval. In particular, we have our properties that we proved in the last few lectures, that the paths of this process are Holder alpha continuous for any alpha strictly less than 1/2, almost surely on any compact time interval. And also, the paths are not locally Holder C alpha continuous at any point for any alpha greater than or equal to 1/2. This is a local property, and so, of course, it's going to hold locally in these versions up here, and therefore in this one as well. Now that we have Brownian motion on the full positive real line, let's think back to the proofs that we gave in the last lecture of these local regularity or unregularity properties here. What played the key role in all of those arguments was the Gaussian nature of the increments there, and therefore the fact that the standard deviation, the average displacement of this increment on the time interval of length t minus s, is of order square root of t minus s. That's what's ultimately responsible for these properties here. So the Gaussian nature of the process plays a key role in determining its local behavior. But actually it's responsible for its global behavior as well. See, it's not just that the increments are distributed as normal random variables, the increments are also independent. And what that means is that the joint distribution of any collection of endpoints, xt1, xt2, up to xtk, is a Gaussian random vector. Processes with that property, which we'll study in a few minutes, are called Gaussian processes, and we can say a lot about those just from the Gaussian nature of the finite dimensional distributions. Now, the nice thing about Gaussian random vectors is that they are totally determined by their mean and covariance. So, let's look at the covariance of Brownian motion. That is to say, for any s less than t, let's look at the expected value of bs times bt. That's the same thing as the covariance in this case. The covariance is defined to be the expected value of the centered versions of the random variables, but Brownian motion is already centered at each time, so this is covariance. We can calculate this quite easily using the independent increments property, just by expanding bt as bs plus bt minus bs. Now, if we break up that sum into two pieces, it's the expected value of bs squared plus the expected value of bs times bt minus bs. Well, Brownian motion is normally distributed with variance s at each endpoint s, and so we know that this expected value is just s. And over here, because of the independence of these two increments, this, by the way, is an increment. It's bs minus b0 will work in the case here where the Brownian motion starts at 0, because we can always translate to get to that case when we start in any fixed point x. These two are independent from each other, and therefore this is equal to the product, expected value of bs times the expected value of bt minus bs, but those are both 0. And so we see that the covariance of bs and bt, in the case where s is less than t, is just s. And by reversing the roles of s and t, we see in general that it is s min t. As we noted, this is the covariance of bs and bt. Now this function of two time variables, s and t, has some nice positivity properties because it's a covariance. In general, if we have any collection of random variables on the same probability space, and we look at their covariance function, this function chi, which takes two time variables and spits out a real number given by the covariance of the process at the two times, that is going to be a positive definite function. Though we should probably use the term positive semi-definite, for a reason that'll be clear in a moment. What does that mean? Here's the definition. A function of two variables is called positive definite if, for any finite collection of times in that set, the matrix which you form by taking the function at any pair of those times, like this, is a positive semi-definite matrix. What does it mean to be a positive semi-definite matrix? It means that it's a symmetric matrix, so M is equal to M transpose, and it means that all of its, therefore, real eigenvalues are non-negative, which can be captured in the following easier to compute statement, that if I take the dot product of any vector xi with m xi, that's always non-negative. Now, we don't really need to think of these things in terms of matrices, although it's often convenient to do so. We can instead just translate these and say that the function chi is positive semi-definite if and only if it's symmetric. Chi of s and t is equal to chi of t and s for all pairs s and t. And translating exactly what this says from matrix multiplication gives us that the sum over s and t ranging through any finite set lambda of chi of s and t times psi of s, psi of t must be non-negative for any function psi from that finite set into the reals. That is, this vector psi can be thought of as a function from n into the reals, giving the components of the vector. Any covariance function is positive definite in this sense. Now, we could take 3 or 4 pages of calculations and show directly that this is a positive definite function, but instead we'll just show that it's a positive definite function because it is the covariance of a collection of random variables. So that's our lemma here. Any collection of random variables on the same space has a positive definite covariance function. Here's why. If I fix any finite collection of times for this general stochastic process here, and I take any function of that finite collection of times, I can just compute this sum, which we need to see is positive. Well, that's a sum over s and t independently of each other, so that's a sum over s, with a sum over t of psi of s, psi of t, and then the function chi is the covariance of xs and xt. Now remember that the covariance function is bilinear. So that means that I can put this linear combination inside the t variable and this linear combination inside the s variable. In other words, this can be rewritten as the covariance of the sum over s of psi of s times xs and the sum over t of psi of t xt. But that's the covariance of the same sum with itself. In other words, it's the variance of the random variable sum over t of psi of t xt. And whatever that random variable is, the variance of it is non-negative, as we needed to establish. Of course, the fact that chi is symmetric follows easily from the definition of covariance as well. So this function, which is the covariance function for Brownian motion, is positive definite. Here's another example, by the way, of a positive definite function. S min t minus s times t. Now, this isn't even positive valued if s or t is negative or greater than 1. But if we restrict s and t to be in the unit interval, then this is a positive definite function. Again, we could do a whole bunch of matrix determinant calculations in order to show that without any understanding of why it's true. Or we could exhibit a stochastic process that has this as its covariance function. And here is one way to do that. Let's let bt, for t just in the unit interval, be a Brownian motion in the usual way conditioned to be 0 at 0. And define xt to be bt minus t times b1. This is a perfectly fine stochastic process. It doesn't have independent increments anymore, and it's not adapted to the Brownian filtration. The value at time t requires knowledge of what the Brownian motion will do in the future at time 1. Of course, this process generates its own filtration that it is adapted to, but it is not adapted to the original Brownian motion's filtration. This is a realization of a process called Brownian bridge. And the thing to note about it is that x0 is 0, of course, because b0 is 0, and we have a 0 here, but also x1 is 0. So this is a stochastic process which has pretty rough looking paths, but it's pinned down to be 0 not only at the beginning, but also at the end time 1. It forms a random bridge crossing over from 0 to 1, although it can also cross under, to be clear. Sometimes it's informally said that Brownian bridge is Brownian motion conditioned to return to 0 at time 1. And of course we could rescale things so that it returns at some other time besides 1, but this is the simplest model. Now, if we had many weeks left in this course, we could do all sorts of fun things with this Brownian bridge. In fact, it will help us to study martingales in continuous time. But for now, all I wanted to do was calculate its covariance function. The covariance of xs xt is equal to the expected value of bs minus sb1 times bt minus tb1. And that is the covariance because this is centered for every t, once again, since it's a linear combination of two centered random variables. So if we expand that out, we have 4 terms. We have the expected value of bs bt minus t times the expected value of bs b1 minus s times the expected value of bt b1 plus st times the expected value of b1 squared. And now we can utilize the calculation we did on the last slide. This is just s min t. This is s min 1. This is t min 1. And this is st times 1. Now, because s and t are both in the unit interval, this is just s and this is just t. And so what we have is s min t minus st plus st, which does indeed give us this. So since this is the covariance function of some stochastic process, it is a positive definite function. Now in both these cases, we have a covariance not just of any stochastic process, but of a Gaussian process. Let's remind ourselves a little bit about Gaussian random vectors. Way back in lecture 26, we talked about them in the context of multivariate central limit theorem. A vector in Rd is called a Gaussian vector, or if we want to be more pedantic, a jointly Gaussian vector. If, well, one way to state it is that its characteristic function has the following form. And I'm going to go ahead and center the random variable first. So it's called Gaussian if it has finite expectation, and after you center it, the characteristic function, that is the expected value of e to the I, xc dotted with x centered, has this form here. It's a kind of generalized Gaussian. E to the minus 1/2 times a matrix times xc norm squared. And referring back to that earlier lecture, we know that if we just expand out this dot product, we can write this alternatively in the form e to the minus 1/2 c dotted with some matrix C times x, where that matrix can be written in the form A transpose. The thing about matrices that can be written in the form A transpose is that they are positive semi-definite, and there's no coincidence that that's coming up here again. And now, just to be clear here, what this means, therefore, without the centering, is that the characteristic function of the full vector x has the form e to the minus 1/2 c dotted with c plus mu dotted with c, where mu is the vector of expected values of the entries of x. So that's a general Gaussian random vector. It's one whose characteristic function looks like this. Now again, if you refer to that lecture, we introduced the Cremier-Wald device, which allowed us to transform questions about weak convergence of random vectors to weak convergence of arbitrary linear combinations of their entries, and putting that together with the central limit theorem, if you like, it's easy to therefore see that an alternative characterization of what it means to be jointly Gaussian is that if you take any linear combination of the entries of the random vector, you get a normal random variable. That is, for any fixed vector xi in Rd, xi dotted with x is a normal random variable. To be clear here, in order for this to be valid, we need to consider degenerate Gaussians here. The point mass at any point is a Gaussian random variable. It's the degenerate Gaussian centered at that point with variance 0. So from this, for example, we can quickly see, by taking xi to be one of the standard basis vectors, which just picks out the components of our vector x, that if x is a Gaussian random vector, its components are all normally distributed. But it's very important to keep in mind that the converse is not true. Having your components Gaussian does not mean you are a jointly Gaussian random vector. You need the joint distribution of those random variables in the entries to also be a multivariate normal. And here's an example to show how that can fail. Consider a random variable x to be a standard normal. And let's take R to be a Rademacher random variable. That is, it is plus and minus 1 with equal probability, independent from x. Then we can take a new random variable y to be R times x. Now y is not independent from x here. It's x times an independent random variable. But, in fact, that new random variable is still normally distributed. Why is that? Well, let's just compute the expected value of f at y for any bounded continuous test function f. So that's the expected value of f of r times x. And now we'll just compute that by conditioning on r. So this is the expected value of f of rx given that r equals 1 times the probability that r equals 1 plus the expected value of f of rx given that r equals minus 1 times the probability that r equals minus 1. Well, on the event that r equals 1, this is just f at x. And on the event that r equals minus 1, this is just f at minus x. But x and r are independent. And so the conditional expectation of f at x given that r equals 1 is the same as the expected value of f at x. And same here. This is just 1/2. This is just 1/2. And now finally note that because x is a standard normal random variable, standard normals are invariant under negation. And so the expected value of f of minus x is the same as the expected value of f of x. And so what I get is that the expected value of f at y is equal to 1/2 the expected value of f at x plus 1/2 the expected value of f at x, which is the expected value of f at x for every function f. And therefore, x and y have the same distribution, which is Gaussian. Great. So I have a vector here, xy, that has Gaussian entries. But it is not a jointly Gaussian random variable. And you're going to prove that on your homework. Now, one nice property about Gaussian random vectors is that they're invariant under linear, in fact, affine transformations. Better yet, we can check if a vector is Gaussian if there's some invertible linear transformation of it that is Gaussian. So if t is some invertible linear transformation, and if t applied to x produces a Gaussian random vector, then x must have been a Gaussian random vector to start. We can see that easily from the Cramér-Wald characterization, because in this circumstance, if I take any vector xi and dot it with x, well, that's xi dotted with t inverse of y. And now I can move the t inverse across the dot product by taking its transpose. Now this is just some new deterministic vector. And since y is a Gaussian random vector, this dot product is therefore a normal random variable. And thus, this is normally distributed for every vector xi, so it follows that x is a jointly Gaussian random vector. In particular, if we take our T to be a permutation matrix, that is, we just permute the entries, that of course preserves Gaussianness. So if we want to check that a vector is Gaussian, we can always reorder the entries however we want and check if that reordered vector is Gaussian. That brings us to the definition of Gaussian processes. Let xt be a stochastic process on an arbitrary time set. That is, they're all random variables defined on a common probability space, taking, say, real values. Such a process is called a Gaussian process if, for any collection of times, the vector xt1 through xtn is a jointly Gaussian random vector. In other words, a process is Gaussian if its finite dimensional distributions are all jointly Gaussian random vectors. Now, by this comment here, it's always enough to check this for t1 less than t2 less than up to tn. Our primary example, of course, is Brownian motion. Brownian motion is a Gaussian process by this definition. Why? Well, fix any increasing sequence of times. Again, by this comment up here, it's sufficient to have them increasing. Now I'm going to apply a certain linear transformation to the process. Let's take this linear transformation of n variables. It's the increment linear transformation. x1, x2, etc. goes to x1, x2 minus x1, x3 minus x2, down to xn minus 1. This is, of course, linear, and it's also invertible. You can write out its inverse explicitly, and we've used this before. T inverse at y1 through yn is equal to y1, y1 plus y2, y1 plus y2 plus y3, all the way up to the last entry being the sum of all of the y's. And you can easily check that if you apply this to here, you recover the vector x1 through xn. So that means that to check that Brownian motion is a Gaussian process, it's enough to check that, of course, the vector bt1 through btn is Gaussian for any increasing set of times. And by this comment here, it's enough to check that t of that is Gaussian for any sequence of times. But t of that is just the list of increments. And in fact, these are all increments because bt1 is the same as bt1 minus b0, where we're taking the Brownian motion that starts at 0 canonically here. But our definition of Brownian motion includes this sequence of increments being independent normal random variables. And if we have independent normal random variables, they do form a Gaussian vector. It's the essentially standard Gaussian vector, denoted by 0 for centered, with covariance matrix T1, T2 minus T1, down to Tn minus 1 on the diagonal, and zeros elsewhere. And that is a Gaussian random vector, as you can easily check by taking dot products with any vector C. So Brownian motion is a Gaussian process. Now what's great about that is that Gaussians are determined by their mean and variance. And so that brings us to the following theorem. Given any mean function C on the time interval and any covariance function, of course it has to be positive definite to be a covariance function, then there exists a Gaussian process on some probability space with that C as its mean function and that chi as its covariance function. Moreover, there's a unique such process in the sense that if two Gaussian processes have the same mean and covariance, then they have the same finite dimensional distributions. We're going to skip the existence part of this proof. It's very similar to the existence proof for Markov processes with a given transition kernel. That is, it's just an application of the Kolmogorov extension theorem, and I'll refer you to the relevant section in driver's notes if you want to see all of the details. For our purposes, we're much more interested in the uniqueness statement. We want to see that if we have two Gaussian processes with the same mean and covariance, then they have the same finite dimensional distributions. Well, since finite dimensional distributions just mean checking the joint distribution of xt1, xt2 up to xtn for any set of times t1 through tn, in order to prove this uniqueness result, all we need to see is that if we have any finite dimensional Gaussian vector, it is uniquely determined in distribution by its mean and covariance. And that is a true theorem, which we can see easily from our definitions as follows. First, let's center the vector. Then, being jointly Gaussian means that its characteristic function after centering has this form here for a positive semi-definite matrix C. I claim that that matrix C is the covariance matrix of the vector. Why? Because this is equal to the expected value of e to the I C dotted with x centered. And if I take the derivative of that with respect to entries Cj and Ck at C equals 0, this is the expected value of differentiating under the integral, which gives us the following. And of course, that just simplifies to minus the expected value of xj-centered, xk-centered, which is the definition of the negative of the covariance of xj and xk. That is, the covariance matrix of the vector x is encoded in the second derivatives of the characteristic function. Well, now let's take the derivatives of this specific characteristic function and see what we get. First of all, if we expand this expression out in the exponent, what we get is the sum over pairs of indices a and b of CAB times CA, CB. And so now we can just take the same derivative with respect to any two variables of that at C equals 0. And I'm going to leave it to you or to your calculus students to compute that and see that it turns out to be minus CJK. So therefore, CJK is equal to this. And this matrix C that we get here is the covariance here. That is to say, if we know the covariances, which we do in this example, we therefore know the full distribution of the centered random vector x. And therefore, to recover its full distribution, all we need to know is its mean. So the distribution of any jointly Gaussian random vector is completely determined by its covariance and its mean. And therefore, if I have a Gaussian process knowing its covariance function and its mean function are enough to recover the distribution of any vector of instances at any times. In other words, enough to recover all the finite dimensional distributions. Now, putting that together with the continuity properties of Brownian motion gives us this result, which was the main application we were aiming for in this lecture. Suppose that we are given a continuous stochastic process, xt, on the positive real line that is Gaussian and centered and has the covariance function S min t. Then that process is a Brownian motion. And the reason is, from the uniqueness result of the last theorem, since xt and bt are two Gaussian processes that have the same mean and covariance, it follows that they have the same finite dimensional distributions. But that means that x is a pre-Brownian motion. It's also a continuous process by construction, and so that means it's a continuous pre-Brownian motion, i.e. it is a Brownian motion. We're going to use that fact to great effect in the next lecture, where we can leverage this easy way to recognize a Brownian motion to construct all sorts of new Brownian motions from old ones via transformations in space and time. And from that, learn all sorts of extremely useful scaling and symmetry properties of Brownian paths.